start the recording and say welcome to everybody for coming along to, I think it's the 36th of these IITE seminars now. So you've been going a good while. And to welcome Adam Clark, who's going to be talking to us about measuring ecological stability. So take it away.
Cool, thank you very much. And I realize this has become something of a pattern now, but I just wanted to add to the large chorus of voices who have said how amazing this whole series is. It's been super helpful for me, starting out at a new university, to feel like I'm still connected with sort of a lot of the theory groups that I knew before I moved out here. And as part of COVID, it's just been absolutely unbelievably useful. So I'm really grateful to all of you for putting this together. And I'm so excited that this has kept on going. So super helpful and really nice tradition. As for the talk itself, this is going to be a sort of grab bag of problems and solutions that I've been fighting with for the last couple of years now. And so I'm going to break this into three parts. The first is going to be to quickly explain what the problems are that I've been trying to solve. I'll then go through three methods that I think we can try to stick together to at least partially solve some of these problems. And then finally, I'll talk about some next steps, some analyses using this combination of methods, and some discussion of what we might be able to do with these. And for anyone who has questions, certainly feel free to break in as we go. Especially for the methods part, it's going to be pretty quick and shallow. So any more detailed questions you have are super welcome. The main focus here is going to be ecological stability, but with a particular focus on coexistence. So I realize stability is a bit of a problematic word at this point, just because it means so many different things. And so I'll try to be specific here when I talk about different kinds of stability. But for the most part, I'm going to be falling within these sort of four general categories of stability metrics. So an attractor, which would be a region towards which dynamics are drawn over time. Resistance, which describes the effect of a disturbance on a system. Return rate or resilience, which describes how quickly the system returns to some previous state following a disturbance. And finally, a basin of attraction, or an attractor block, so a region of space which draws dynamics in towards it, which dynamics tend not to leave once they've entered it without some sort of a transition taking place. And on the left, there's sort of this classic figure of how we might imagine complex dynamics playing out in a landscape with multiple equilibria and multiple basins of attraction. And that's sort of the starting point for the problems that I'm dealing with. So I'm now out here at the University of Graz in Austria, on the southeast side of the Alps. This is a picture of the Quaim. This is a relatively low alpine meadow right on the border between Styria and Carinthia. This picture is taken a little bit under 2,000 meters, looking out over the pasture. And this is an area I've been going to for most of my life. And it's also well known among botanists in the area as being one of the more botanically diverse regions in this part of Austria. So if you go out at this time of year, you're likely to find orchids, all kinds of wildflowers, more species of festuca than anyone ever needs to see in their lives, and all sorts of other interesting plant and animal life. And so it has this feeling of a conservation landscape, but at the same time, it's very heavily used. So this system itself wouldn't exist if it weren't grazed. This picture is literally taken from the same spot as the previous picture, but just turning the camera about 45 degrees. So here we're under the tree line in this system. If it weren't grazed, most of this area would revert back to forest quite quickly, and we would lose this landscape. And so in some ways, this system here is something that we might think about as a community. I would imagine that it would be reasonable to describe these species as coexisting, but it doesn't really line up with the classic ideas of stability in terms of a fixed point equilibrium towards which things are drawn, because without this disturbance regime, we would lose this system. And so I've been thinking for a while about how we could go about more consistently coming up with a quantitative definition for how we might talk about that kind of a community. So one where it persists over space and time It has certain properties that we can measure and that we can identify consistently, but it isn't really stable in any of the mathematical senses we might usually use. As a more specific example of this problem, I just want to show a little bit of work from Cedar Creek. So this is where I did my doctoral work. This is a tall grass prairie system in the central northern part of the United States. And the landscape here is sort of this nice patchy mix of different landscape types. So here, these are old abandoned agricultural fields, old fields, which I'll be talking about in the next slides. But this is sitting inside then a matrix of other landscape types. So here you have a nice forest. We have wetlands. A little bit farther south, there's a big range of oak savanna, some of the last oak savanna in Minnesota in this area. And so again, just like the ostrich systems I was talking about, this is a system with a lot of transients. Probably a system where without some kind of disturbance, things would tend towards forest over long periods of time, but importantly also a system where grasslands tend to persist for very long. So there are old fields here which haven't been burned or plowed in a century and are still generally open grasslands. The general pattern that we see, so how do dynamics play out in the system, looks something like this. So here on the vertical axis on the left is biodiversity, and the vertical axis on the right is the productivity, so the biomass production per year in this system. The horizontal axis shows the age of the system, so how many years it's been since this old field was last plowed, since the last big disturbance event. And this shows sort of two important patterns. The first is that in both of these metrics, we see recovery. So the black dotted line here at 100% is an estimate of what the biodiversity and productivity in these systems were prior to agricultural use based on nearby oak savanna parcels. So we see that we recover back towards this rate, towards this initial state. But you'll see after 100 years, we're still not all the way there. And in fact, for productivity, we're not even halfway there. So although the system is undergoing some kind of successional dynamics, even at the very oldest fields that we see in this chrono series, there's probably nothing approaching what one might think of as the climax state. So even if you believe in climax states, this system almost certainly isn't there yet. It hasn't returned back to whatever we imagine it would have been prior to these sorts of major disturbance events. In order to sort of get a better handle on where the system might be going, one thing you can do is take the same dynamics, but break them up into different estimates across different scales. So here, these are the same data, same set of old fields. These three rows here show dynamics for three major species groups. The top are annual plants, the middle are C3 cool season grasses, and the bottom are C4 warm season grasses. And these in the middle, these figures just show the overall average biomass in these systems. The polygons shaded here in different colors show the average dynamics in these systems over time. And the gray lines show the dynamics that we see in the individual fields that have each been surveyed in that area. I've taken off the axis labels here just because the actual quantities aren't very important for what we're talking about. But basically, as we go from left to right, we go again across old field age, so starting at abandonment all the way up to about 100 years. And then the vertical axis is just low biomass to high biomass. The figure on the right, finally, these three panels, is an estimate of the stability of these three subsets of species. And in this case, I'm using a proxy based on invasion rate. So this is effectively an estimate of the ability of these species to invade an empty patch from low abundance. So invasion when rare, basically. But it's important to say, I'm not just going to pick on the invasion rate here. The results are quite similar if you use other common metrics. So you get similar mixed results if you use eigenvalues and asymptotic stability. You get similar results if you look at persistence. For our purposes, though, the important part is going to be red colors indicate a lack of stability. So in this case, that the species aren't able to invade patches from low density, and the blue colors show stability. So the system can be invaded from low density. If we look at the beginning of the time series, so this first vertical slash here, we see, consistent with sort of biological expectations for the system, annual plants come in very quickly at high abundance, whereas the C3 grasses and C4 grasses don't. And that also manifests in these stability estimates. So panel A on the right shows the stability of our annual plant species here. We find that they're able to invade patches from low density. They're able to increase in abundance in the system. Whereas for the C3 and C4 grasses, that's actually not the case under most circumstances. And I should add here, the horizontal and vertical axes here are showing the scale at which we observe these dynamics. So this is effectively how many years of data are we looking at once on the horizontal axis. And the vertical axis is how many square meters of spatial surveys am I including in my estimate to calculate the stability metric. And this shows that if I'm only looking at short time spans, over most reasonable spatial scales that I would go about surveying the system, I would not identify either of these C3 or C4 grasses as being stable in the system, being able to invade from a rare state. If I look at intermediate time periods in this dynamic, the pattern changes again. So here the annual plant species begin to drop out. The C3 species now show up as blue, so show up as being stable in the system, and the C4 grasses at the bottom are still red, still not able to invade. And then finally, at the very end of the successional time series, we have stable dynamics for the C3 and C4 grasses and a lack of stability for the annual plants, which makes sense given the fact that the annual plants are being pushed out of the system over time, whereas the C3 and C4 grasses tend to be establishing persistent populations in these systems. So the main point here is it seems like it would be very hard, based on the smaller amounts of data that we tend to have available to us in these kinds of systems, to actually come up with anything approaching a complete picture of what the possibilities for stable coexistence might be in this system. If I were to have just looked at short time series, I would probably not have successfully realized that the C4 grasses and C3 grasses are able to persist in this system. If I'd looked at even relatively long time periods, so up to 10 years, I would have still thought that only the C3 grasses were able to persist in the system and the C4 grasses weren't. And it's really only over this almost 100-year trajectory that we're able to look at with something like 500 square meters of surveys that we really start to be able to eke out even this super simple pattern, which is basically just classic ecological succession in a tall grass prairie. And this becomes a bit more concerning when we want to do something more general. So what I was just talking about with this grassland system is sort of this intermediate case here, case B. And here we sort of have, in these areas that we tend to survey, a nice mix of individuals. Dynamics tend to proceed at a relatively nice rate for us, and that if we come out and measure a system every year, we sort of can expect that the system has changed a little bit, but not too much, so we can fit it nicely to models and track dynamics. On the other hand, though, if I survey forest dynamics, anyone who's worked in forest plots knows that two big problems you have are that you need enormous spatial scales in order to get a good estimate of the overall diversity in a region, but you also need a lot of time. And that's because the turnover in these systems can be 20 years, 30 years, 40 years. And so it can honestly take longer than the career of the average ecologist in order to go out there and get a good sense of what dynamics are in that system. And for things like microbes, you in some ways have the opposite problem. Even at the very smallest samples we can take, you end up having enormous mixtures of individuals, where it's hard to decide whether all of the individuals that you've collected in your sample really have an opportunity to interact with each other. So there's really a community, or rather a mixture of communities. And even if we sample at the fastest rates that we're able to now, given time and money and technical considerations, we still often have the problem that the communities change so much between survey intervals that we don't really have much of a handle on what the dynamics between those intervals could have been. And so this is sort of where I've been stuck for a while in terms of trying to think whether it would even be possible to come up with a metric or a series of metrics with which we could quantify the degree to which we think a group of species is coexisting, make some estimate as to whether we think that group of species might actually be able to persist in the long run. And also whether we might be able to come up with a set of metrics that would work relatively well across lots of different types of species, so lots of different sites and lots of different systems. And so to sort of summarize that a bit, given that ecological systems are complicated and that estimates of stability are highly context dependent. They'll change across space and time and species groups and locations. How can we go about monitoring, managing, and conserving ecological communities in these systems? Make estimates of something like how long before species X goes extinct, or what will happen if I reduce the size of this reserve by 50%. Can we find a general way to quantify this stability that works across lots of different real-world systems? And finally, can we try to link these methods to a lot of the existing theoretical frameworks that we have out there? Because I think if there is one problem we don't have in stability right now, in ecological stability studies, is not a lack of theory. We have huge amounts of theory, of very, very well-developed theory, I should say, based on stability analyses, persistence analyses, permanence theory. There's all kinds of good stuff out there. And so rather than just coming up with a new theoretical metric, I think it's super important to find a way to connect to the existing suite of research that we have while trying to address these questions. So that's sort of the problem statement for today. And I'm about to jump into these individual methods that I think might help solve it. But before we do, does anyone have are there any questions or maybe complaints? Everyone doing okay? Excellent. Okay, see thumbs up. Then let's jump on in. So first, these three methods I'm going to talk about is Taylor's power law. And this was sort of reintroduced to me back when I was in IDIV in Leipzig by Peter Kiel, who pointed out at a lab meeting at one point that it was interesting that Taylor's power law is one of the most, like the species area curve, it's one of the most commonly observed patterns in ecology. But what he mentioned that I'd never thought of before was that maybe the fact that it's such a common pattern might be useful for statistical analyses. So if we sort of assume that we're likely to find it in a system, maybe we can leverage that fact in order to simplify our statistical analyses in one way or another. Just as a short introduction to the Taylor power law, it's a relationship between sample variance and mean, which is a power relationship. So like the function here, the variance is related to constant c times the mean raised to a power z, and it's often written in log space like this. And when you write it in log space, you get a nice linear function like this one over here. And like I said, the most interesting thing about this pattern is that it shows up in almost any system that you can measure, and the fits are usually very good. So if you go out and measure this in the real world and go calculate R squared for this mean versus variance relationship, it's pretty common that you get an R squared upwards of 90%. So quite similar to the species area relationship in that you tend to find it everywhere, and it tends to do a very good job phenomenologically describing patterns. As some of the examples of places where it's shown up, it's been used to model chromosome size distributions, stock fluctuations, bird dynamics, traffic flow problems, and all kinds of other things. So it's not just limited to ecology. It's one of the rare cases where ecology seems to have gifted something to pure math and physics, which is sort of nice. But in any case, very widely used, very widely observed pattern, and a very consistently maintained shape to that pattern. The way that we would go about measuring this in ecology might be something like this. So here we have this landscape up in the Alps, and we would go out and put a series of plots over that landscape. And with in each of those plots, we would go and measure something over time. So maybe the abundance of a particular species. We measure that abundance year after year after year. Based on that resulting time series, we can calculate a mean and a variance for the abundance of that species within that plot. And then we can plot something like this. So this is the relationship between mean and variance for Schizopyrium scoparia. This is a little bluestem, which is one of the C4 grasses at Cedar Creek that we saw a few slides back. And you see here, if you plot them against each other, you get this nice linear relationship in log-log space, an R squared of 86%. And I should say this is literally just the first species that I pulled data up on. So I didn't pick the species that fit the pattern the best. I picked the first species that I happened to have loaded in my computer in order to make this figure. And it would look similar for pretty much any other species that you would try to graph such a relationship for. There are a lot of interpretations for why this pattern should exist. I'll quickly talk about the most common, and then I'll talk a bit about why it's a bit more complicated than that. But if you imagine some variable x, which has a mean and a variance at the level of a single plot. The way that you would get the average abundance across some subset of those plots, so across a set containing several plots, would be that you just sum up the individual average values. So it would be A times the initial plot level mean, where A would represent the sampling area or sampling time or whatever else it is you're trying to average across. So this is how I would calculate the average abundance across some group of plots. Similarly, for variance, there's sort of two extremes that can happen. If we imagine that the plots have totally independent dynamics from one another, so the patches are totally asynchronous, then we can simply sum up the variances. So the variances of the abundance of the species in plot 1 plus plot 2 plus plot 3 plus plot 4 and so on is just the variance in plot 1 plus the variance in plot 2 and so on. So we end up with just A times the average plot level variance in this case. And if we end up with a relationship like this, then the expected slope of the Taylor-Power law relationship is 1. So we expect a slope in that log-log graph of 1. In contrast, if we imagine that the plots are perfectly synchronous, so they all follow exactly the same dynamics from year to year, in that case, the formula for variance looks like this. The variance of the group is simply A times the variance of A times the plot level abundance, which gives us a function of A squared times the average plot level variance. And if this is the case, so if the plots have perfectly synchronous dynamics with one another, then the expected slope of this mean variance relationship in log-log space is 2. And so in some ways, this gives us this nice bounding of this power law function. So here's again this empirical data for Schizocurium scoparium. And here, this top line at z equals 2 would be the expectation if these plots all had perfectly synchronous dynamics. Whereas this bottom line here is the expectation if we imagine that the plots have totally asynchronous, I shouldn't say asynchronous, that's hard when you have lots of plots, but totally uncorrelated dynamics from one another. And given that the actual slope is closer to 2 than 1, I guess we could say, based on this pattern, that the plots are more close to being correlated with one another than they are to being uncorrelated with one another. So they're closer to being perfectly synchronous than they are to being uncorrelated with one another, which makes sense for biological dynamics. They're probably responding to the same kinds of climate and disturbance variables from year to year. The problem with this is that if we look at these scaling coefficients across lots of different systems, we actually find ranges of values that fall well outside of this range of 1 to 2. So these are actually just the values in the original paper published by Taylor, where he introduced this pattern. And so 5% of the data sets he presents had scaling coefficients of less than 1, which would, in that simple interpretation, mean they're less correlated than perfectly correlated, less correlated than perfectly uncorrelated. And 20% of the data sets had a scaling coefficient of greater than 2, which I guess would mean that they were more correlated than perfectly synchronous. And so obviously the simple explanation is missing something. And indeed, if we now dive into physics, which has analyzed this problem a lot more deeply in the last couple of decades, here the Taylor scaling coefficient is listed as P. In physics, they call these Tweedy distributions. But we find that depending on the underlying stochastic process driving the variation in the system, we can actually get lots and lots of different scaling coefficients, depending on the system that we're analyzing. And so basically this is to say, like lots of things in ecology, it's very complicated, and it's going to be very hard to try to specifically predict what exactly is driving a particular scaling coefficient that we happen to observe in the real world. The other issue, if we want to look for a mechanistic interpretation of these patterns, is that there have been so many that have been posited and that fit the data very well. So, for example, there were papers already in the 60s suggesting that this, and this is actually from the Taylor paper, I should say, suggesting that this pattern arose due to aggregation of species in space. Others have suggested that this is due to something related to temporal synchrony and disturbances, or something about fractal structure of landscapes or species distributions, or an inevitable result of species interactions. or that it's just a statistical artifact that you can't avoid in dynamical systems. I should say dynamical systems that can't drop below 0 in their values. And so the result of all this, of the sort of flurry of different mechanisms that have been posited and that all seem to fit the data equally well, has been a somewhat unique pattern in ecology, which is that the numbers of citations related to Taylor's power law have actually declined over time. So like just about everything in ecology from the 80s to the 2000s, we had this exponential rise in the numbers of papers per year written about Taylor's power law. But since then, it's actually been dropping every year. And I don't know a whole lot of topics in ecology for which this is the case. But my interpretation of this is that people are sort of giving up on this particular description. And I should say the reason the dragon is here is twofold, that I think it kind of looks like the shape. So that's also where the title comes from. This is sort of a very alluring thought that we can use the Taylor power law to say something about dynamical systems, but it seems to have some lurking danger which prevents us from solving the problem. So that's the first piece. It sort of looks like a dragon. The other is, I know it's very hard to add anything approaching humor or levity to a theory talk, and so this is your humor and levity for today, and I hope you like it. But in any case, so people seem to be giving up on this particular pattern. I would argue, and this is going back to Peter's comment at the beginning of this section, this probably suggests that the best way to think of the Taylor power law is basically as a heuristic pattern that we can take advantage of in the same way that we take advantage of a normal distribution. So we know a lot of different processes will cause my data to be normally distributed. So just because my data are normally distributed, I don't necessarily know why, but I can take advantage of the fact that they're normally distributed in order to do a lot of powerful statistical analyses in order to simplify the ways that I can handle my data. And so similarly for the Taylor power law, I think it's unlikely that we're going to be able to figure out why a specific data set has a scaling coefficient of n under 2. But given that it's conserved, we might be able to take advantage of that fact in subsequent analyses. So that's our Taylor power law. And as a summary, Taylor power law is a general pattern relating the mean and variance for ecological processes. The slope of the law, which is usually z in ecology, but is p in physics, summarizes how variance changes with abundance. And finally, there are lots of different types of random processes and mechanisms that can lead to identical z values. Next, I'm going to drop us into the coefficient of variation, the CV. This is something I'm sure you all know ad nauseum at this point. So I'll go through this pretty quickly, but just as for form's sake, the coefficient of variation is just the standard deviation of some process divided by the mean. And it's often proposed as one of the simpler ways that you can summarize stability in an ecological system. So CV equals 1, for example, implies that the standard deviation equals the mean. CV equals 2 implies that it's twice the mean, and so on. So as the CV gets bigger, the system gets more variable relative to its mean value. And I should say this value is also often summarized as invariability, which is just 1 over the coefficient of variation squared. And that has the advantage of increasing as systems get more stable. So it's a bit more in line with some of the other linguistics that we use to talk about stability in ecology. Just as some examples of how these processes look, here we have 4 different processes, and depending on how the means and the standard deviations change, we can have, for example, 2 processes with very different standard deviations, but the same coefficient of variation. And so let's say 2 processes that have similar means, but different coefficients of variation, and so on. One of the problems with coefficient of variation is that it's largely qualitative. So when we report it in most papers, it's not really supposed to be some sort of a definite statement about the absolute stability of a system, but rather we might use it to compare lots of different systems and talk about their relative stability. So how stable is system A relative to system B? One other issue is that it does tend to mix lots of different sources of variation, some of which we probably would all agree don't have a whole lot to do with stability, but I'll talk about that a bit later. More importantly for our purposes here, though, there have been a lot of really exciting advances in how we can think about coefficient of variation and what we can do with it. And so just as an example here, there have been a whole flurry of papers, largely led by Jeff Arnoldi and Bart Hagemann, just so that I can embarrass them a bit and I would say if anyone has not seen these papers, you should like leave this talk right now and just go read them. But in my opinion, these are some of the most important advances we've had in empirical understanding of stability and ecology in my lifetime. But effectively, they've shown that there's a lot of ways that we can relate the coefficient of variation, which we can measure quite easily, to a whole bunch of other theoretical metrics of stability, which are generally much harder to measure. And so here's sort of this canonical formula if I'm relating coefficient of variation to the resistance in a system and the resilience in a system. And there are, of course, a lot of assumptions you need to make in order for these relationships to hold. But nevertheless, they suddenly give us this ability to take CV, which is something we can measure, and relate it to a bunch of theoretical metrics about which a whole lot of previous work has been focused on. And just as I would say, this is the two papers I would suggest jumping into if you haven't run into this work before to get sort of a first pass at the results here. A related set of advances relating to coefficient of variation relates to scaling theory. And so this is a paper from Xiaoping Wang from 2017 in Nature Communications, which I think arguably sort of kicked off the ball on this. And there have been a whole bunch of other similar studies since then, which have taken advantage of very general statistical scaling rules to show how we would expect coefficient of variation to change over space and time. So again, this is super helpful because it means we can take coefficient of variation, which is a quantity we can measure, and make some estimates about how we think that quantity might change across different temporal or spatial scales. And so these two halves, this thing that allows us to link coefficient of variation to other theoretical metrics and this ability to scale coefficient of variation across space and time, jointly means that we actually probably can do a whole lot of really powerful theory based on these empirically tractable metrics. Another nice thing is we can actually relate CV directly to the Taylor power law. And so you remember the Taylor power law up here is this relationship between variance and mean. And given that CV is just the standard deviation divided by mean, we can find a link between those two. So if we basically assume that the Taylor power law holds and then plug that relationship into the coefficient of variation, we end up with this scaling law right here, which would be the amount that we would expect coefficient of variation to change within a system where a particular Taylor scaling coefficient holds. And this is quite similar to the scaling coefficient derived in the Wang paper. And so if we were to interpret these directly, it would basically say if z is less than 2, so if the scaling coefficient is shallower than 2, we would say that the system becomes more stable at larger scales. If it's greater than 2, the system becomes less stable at larger scales. And if it's equal to 2, then stability should be scale invariant. So nice direct analogy that we can draw between these two metrics. And as a summary, quickly, of our coefficient of variation, so it's a metric that we can use to summarize the relationship between mean and variance. We can mathematically link it to the Taylor power coefficient, as well as a whole bunch of other theoretically useful metrics. These arguably can yield a scale invariant estimate of stability that we can apply in other systems. But we're going to have two important assumptions that we're going to have to get around still. The first is that, at least for existing frameworks that use coefficient of variation, the assumption is that we're looking at variability around some fixed point, so a single fixed point equilibrium. And the other piece is the theoretical work that I was showing you relating CV to other metrics is largely based on analyses of white noise perturbations around a fixed point estimate. And so things, for example, like observation error or internal system dynamics that aren't linear aren't built into this framework yet. So these are two things that we would have to deal with if we want to apply these methods to more complicated kinds of ecological systems. All right. Finally, to take us into the last of these methods, I'm going to talk very briefly about stochastic filters. Stochastic filters directly solve the first of the two problems I was talking about here. And that's this conflation of different sources of variability. And so sort of obviously, if we have a time series like this one down here in the bottom right, there's probably a whole lot of different sources of variability that are contributing to the overall variation we can see. Part of that is going to be observation error. So that's just the differences between the actual values of a system and the values we measure due to imperfect measurement. There's also internal system dynamics, so something like predator-prey oscillations, which although they cause variability over time, aren't necessarily indicative of a lack of stability. And then finally, we would have underlying process noise. And that's what I would argue is actually the real thing that is related to stability that we care about. And so that would be underlying variability that isn't part of underlying dynamics or observation error. And just my heuristic definition here is basically going to be variability that is not predictable in the short term based on past behavior. For anyone who's a bit skeptical at the notion of deterministic dynamics that are still consistent with stability, there's a really nice paper that came out a few years ago in Nature showing long-term stable oscillations in a predator-prey system within a mesocosm, I think, in this case. And so I think this is particularly exciting for two reasons. The top panel just shows that the predator and prey species managed to persist together for a long time. So basically for a year, which is hard to do for anyone who's tried to do predator-prey experiments. They certainly know this. The bottom panel, though, is what for me shows that this is almost assuredly a stable oscillation. And what this shows here is how the period length changes over time. And a few times the period length gets knocked off of this fixed cycle, but it's able to reestablish itself over and over and over again. And so what this is showing, it's not simply that these species persist, but rather the actual oscillatory cycle of these dynamics is stable. It's an attractor, and the system will be drawn back towards that pattern even after disturbance events have knocked it off of the initial oscillatory phase. So I'd say this is what I mean when I talk about deterministic dynamics that aren't indicative of instability. To separate these different kinds of variability out, so deterministic dynamics, observation error, and process noise, there's a really well-established set of tools which sort of fall under the general umbrella of state space modeling. And what state space modeling basically does is it models two different states of a system. X describes the true state of the system, which is unobservable, and Y describes the noisy observations of the system that we're actually able to make. And we then divide these dynamics up like this. So we say that the dynamics of X are some function of its past state plus W, which is a process noise function. So that's that true stochasticity that actually influences the state over time. And then our observation of the system is just equal to the true state of the system plus V, where V is our observation error function. The challenge here is that we need to know these functions. In particular, we need to know f of x. So we need some function which will predict the abundance of a species, for example, in the next time step based on its abundance in past time steps. And one of the more general problems that people encounter in state space modeling is depending on the function you choose for f of x, you can get lots of different answers from an analysis like this. So you tend to pass variability back and forth between the dynamical variation function and the process noise function, just depending on how you happen to design your model. One way around this is to avoid parametric modeling and take advantage of some kind of non-parametric method. What I'm going to advocate here is a series of delay embedding methods based on Takens theorem. And to just describe this very, very briefly, this is a sort of suite of mathematical tools which take advantage of the fact that future dynamics of a system can generally be predicted based on some combination of its past behavior over time. The method is semi-mechanistic in that it's not just based on past lags of a single variable, but you can actually put it together based on lags of multiple variables and get some estimate of what the interaction strengths between those variables are. But critically, you don't need any underlying function. You don't need to have any a priori knowledge about how the variables are coupled in order to make predictions. The method is also guaranteed to perfectly match true dynamics given an infinitely large training data set. So that's nice. We know that as we get more and more information about the system, these methods are guaranteed to converge towards the true estimates of future states. Just to sort of demonstrate roughly how this method works, imagine again we have predator-prey dynamics here. If I were to tell you that the current state of the prey is 5, so as we see right up here, it's not actually possible to predict the next state of the system, because from a state of 5, the prey abundance can either decline or it can increase, depending on where the predator happens to be. So if I want to know what my next state will be, given that the prey abundance is 5, you actually also have to tell me whether the predator is abundant, in which case the prey is about to decline, or the predator is rare, in which case the prey is about to increase. One of the really useful bits of insight behind Takens' theorem is that it shows that we don't actually need to know anything about the predator in this case. We can just use information from the prey species as a proxy for the predator dynamics. So here, if I know that the current state was 5 and the previous state was higher than 5, I know that I'm in a downswing and the next state will be lower. Whereas if the current state is 5 and the previous state was lower than 5, then in the next state I'm going to have an increase again. So this is a really simplified version of this. This then tracks up to higher dimensions and lots of different coupled variables. But in general, you can think of this as a nice, robust way to make non-parametric estimates in complex systems. These methods have already been coupled with state space models. So this is from a series of papers by Franz Hamilton in what he calls Kalman-Takens filters, which is a non-parametric extension of state space modeling that applies Takens' theorem as a replacement for this f of x function. And what it effectively does is create a moving central tendency for the system. So you can almost imagine this like nice old ball and cup model that I showed at the beginning of the talk. But rather than assuming that this ball and cup model is stationary, it's actually moving around through time. And now our process noise function is showing how much jiggling we have back and forth around this central tendency. So this is nice, because in some ways, this now allows us to treat a complex dynamical system as though it were a fixed point linear system, because we basically just keep on tracking a new central tendency over and over again through time, and we can linearize the system around that moving point as a simple proxy. And my hope is that we can begin to start applying some of these more theoretically detailed methods based on coefficient of variation inside this kind of a framework. So I said the Kalman-Takens filter already exists, has been presented in a series of papers published over the last 5 to 10 years. One disadvantage is that Kalman filters tend not to hold for complex noise functions, which you actually sort of need in ecological systems just based on how dynamics change as you get close to 0. There are extensions of this, though, of Kalman filters called particle filters, which are based on Bayesian MCMC optimization methods. And these allow a much more flexible approach for modeling the different noise functions. So these haven't had Takens filter, Takens dynamics integrated into them yet, but I'll show some code near the end of this talk that have begun to do some of these analyses in a more flexible framework. So final summary for the method section here. State space methods and stochastic filtering allow us to separate different sources of observed variability. These can be combined with non-parametric methods, such as Takens' theorem, for cases where we don't know underlying dynamics, but still want to separate out different sources of variability. I would argue this probably lets us compute coefficient of variation, in particular relating process noise to coefficient of variation in a way that can be linked more directly to stability, even in a complex system. But we're still very early on in this process. So there are a couple tools now which will let us do this, but not a lot. And the tools that do exist are not particularly well tested yet. Finally, to drop us into the very last section here, the bits I've shown here, just as a quick rehash, are that the Taylor power law is a general pattern that links changes in abundance to changes in variability and applies in lots of real-world systems. The coefficient of variation is a metric that quantifies variability in empirical data, which we can measure in most systems and can be linked to a lot of different theoretical concepts. And then finally, there are various stochastic filtering approaches, which can be applied to estimate coefficient of variation and separate the effects of observation error, process noise, and deterministic variation. And so by joining these three methods together, I think that we can build some general purpose tools for quantifying stability in real complex systems. And the tool that I've been working with that does this, so this is by no means the same as the only one out there, is something I've called the particle Takens filter, as a nod to Franz Hamilton. And so it's just an extension of the Kalman filter that uses a particle filter to allow for more complex error functions. And in the default version, it models observation error as a fixed fraction of abundance. So it effectively assumes that there's, for example, a 10% sampling error or something like that in the system. And it then models the effects of process noise following the Taylor power law. So where we have a function relating the strength of process noise that's proportional to some constant times the mean abundance raised to a power z. But the nice thing is, since this is solved using an MCMC solver, it's actually pretty easy to change these. So for anyone who has other favorite functions that they want to stick into these, you can stick those into the MCMC solver as well. The way that the analysis looks sort of plays out something like this. So imagine the black line is true dynamics over time, whereas the orange points are noisy observations of those dynamics. We then decompose the noisy observed dynamics using a delay embedding model. So here we take 3 different time steps of the observed abundances. The gray lines show that trend that we observe in the noisy data. And the black line shows the actual abundances. These are the averages that we get from these noisy trends. We can then use this model here to predict future states of the system. So here's our prediction from this Takens model versus the true abundances of the system. And you'll notice they're not the same yet, and that's because we haven't accounted for stochastic variation. And finally, in order to quantify the effects of these different sources of variability, we apply the particle filter itself. And so effectively what a particle filter does is it simulates a swarm of different potential states of the system, and then usually resamples from within that swarm so as to maintain a relatively dense likelihood surface. And so if we start here, for example, we start with some estimated point from the model, and then we simulate lots of potential next steps in the system based on our deterministic function and some hypothesized process noise function. And that now gives us a new distribution of potential values due to process noise and a distribution of the likelihood of various observations given our observation error function. We then basically take the convolution of those 2 functions in order to get our estimate of the true state of the system in the next point in time. And we then posit lots of different observation error and process noise functions in order to fit our model to the data. I think I'll actually jump over this and just show a result from this analysis. So here's an analysis of microcosm data from a paper from 2011. Here the polygons show our estimates of the abundances in these 2 states, I should say. I think this is a high temperature state and a low temperature state within this system. So the top row shows that we're able to sort of make an estimate of what the likely abundances are based on noisy observations, which is sort of a nice side effect. But more importantly for us is the side panel here. These are estimates of the different sources of variability in the system now. Here at the top are estimates of the strength of observation error in the system. And then these are our estimates of the intercept and the slope, or the scaling of the scaling coefficients of the Taylor power law in this system. And this is very nice because it actually relates quite closely to the predicted and observed times to extinction in this system. So you'll see over in this case, in case A, which relates to this function over here, we have a quite long time to extinction. So from the modeled estimates, we expect that this system would probably persist something like 1,000 days before an extinction event occurs on average. Whereas here for position D, as is pretty obvious from the time series, since it peters out around here, we expect an average time to extinction of a little bit over 500 days. And that actually plays out nicely in these scaling coefficients here. So for the system that persists longer, we have a lower scaling coefficient. And for the system that persists for a shorter period of time, we have a higher scaling coefficient. You remember that the higher scaling coefficient effectively says that the system becomes less stable as abundances increase. And as a nice sort of summary for how this looks. So here again would be this is just a graph showing how for abundance and different scaling coefficients, we expect the overall strength of process noise to change over time. And this is, I guess, my last takeaway for the talk. And I suspect something like this could be a really useful general tool for lots of different ecological systems. But it basically shows if we have a scaling coefficient of 2 here, then as the abundances increase, we find more and more variability. And here, these shaded contour lines also show us the probability of an extinction event taking place in the next time step. So effectively, as abundances go up, extinction probability goes up. Whereas if we had a scaling coefficient of lower than 2, then as abundances go up, extinction probability declines. But critically, for very low abundances, we actually end up with a quite high extinction probability. And so this shows nicely, depending on various combinations of what your abundances are and what your scaling coefficients are, you have different expectations for time to extinction for different types of dynamical regimes. So as next steps, for anyone who wants to play with this themselves, the code for all of these analyses is uploaded here at this GitHub repository. At some point, I will put it out as an R package, and I also have a preprint that I've been promising to post at some point. So I will do that soon, and that will also be available on my website. And I'm working on some applications of this. For anyone who is interested in talking about this, I would be delighted if you reached out. Even if you think that it's deeply stupid or that somebody else did it 30 years ago, that would be super helpful for me to hear. So here's my contact info. Like I said, my website here, where the preprint and code will be available. And if you know of other similar methods, I'd be super grateful to hear. And then this is my long list of people who have helped me in the process of putting this together. This has been a very long and slow process for me. So I'm very grateful to all the folks who've had a lot of patience teaching me new methods and helping me fight through various bits of code. So thank you very much. And that's the end of my talk. So if anyone has comments or thoughts, I would love to hear them.
Thanks very much. Yeah, so if anyone has any questions, just raise your hand in the chat list on the reactions button down the bottom. And ask all. So Abdul, would you like to ask a question?
Yeah, hi, so thanks for the talk. I just have a question about Taylor's power law. Does that result still hold in unbounded systems where you can have either positive or negative values?
That's that. Yes, thank you for asking that. No, the thing that it applies to is processes that are bounded above zero.
Right. Okay, so then I mean,
it seems to show up in almost any dynamical process that is bounded above zero. But if you're allowed to have negative values, then it disappears.
Right. So I mean, I guess if there's a correlation between, say, the mean and the quartile it finds itself in, right? Like as you increase the mean, it's probably going from like the 50th percentile up to like, at infinite values closer to the 100th percentile. So wouldn't you expect to see this just generally based upon any unbounded, any finite, any positive unbounded distribution?
Yeah, and so that's actually the last of the papers I had in the list there. The statistical inevitability is basically getting at that, in that it's the reason it shows up everywhere is that it's impossible for it not to, for a bounded process. And so I think the surprising part isn't that it happens. The thing that's helpful is that it seems to be pretty conserved across space and time. And so, like I said, just like it's not surprising that data ends up normally distributed for all kinds of processes, because it just kind of has to. But once we know that it's normally distributed, we can sort of assume that it will keep the same distribution, at least for a while. And so rather than having to work with the whole messy data set, we can just abstract the data set as a normal distribution, which we can describe with 2 parameters. And so I think the Taylor power law is similar in that sense, that we know it has to be there. We desperately hope that it's conserved. And so maybe it lets us get away with describing our systems in a low parameter abstraction rather than having to keep track of the whole time series.
Gotcha. Could I ask a sort of follow-up question to that then?
Yeah, please.
What do you expect to happen if you don't see it conserved in a system? Like,
I would go out on a limb and say that it means something about the underlying process has changed. I don't think it's ever going to give you any more than that, just because we know there are so many different processes that can influence it. So it's not like if the slope gets steeper, it means competition is becoming more important or something like that. I think rather than trying to pull meaning from changes, to me, the more important thing would be to try to figure out how quickly they happen, and then to try to measure them. So to see if there's some way that we can build that change into our predictive model. But I suspect that prediction of the change of the Taylor power law over space or time would have to be entirely phenomenological. It couldn't be based on some underlying mechanistic expectation.
Gotcha. Thank you.
Thanks a lot. Are there any other questions from anybody?
Hey, I have a question, if that's okay. Yeah. So Adam, thanks for a great talk. I just have some like conceptual questions about the type of stability that you're like looking to, like that you're interested in, because I was just thinking, like, if you have, let's say you have like some like deterministic or like some trajectory over a very long time period, and then you have like noise on top of that. Like, because like in my mind, what I'm, you know, when I think of stability in like ecological systems, I mean, what I mean when I think about that is like, okay, we want the system to be stable. Like, we don't want species to go extinct in the long term, right? But then you have like some noise on top of that, maybe, you know, that from year to year variability. So like, is that what you're trying to disentangle, like that noise on top of like some trajectory? Or
So I think it's much more, for me, the point is more that for a lot of, we know that in most systems, there is a trajectory. But I think it's maybe definition first would be yes. The thing I'm most concerned with is, will this community still be here in 100 years?
Yeah.
I think in order to make that prediction, from the systems I've worked in, it turns out that the perturbations are as important for maintaining the system as the dynamics are. And so I think simply assuming perturbations, higher rates of stochastic flux, whatever, are associated with lower stability probably isn't going to be right all the time. And so for the grassland systems I was talking about in the beginning, absent those perturbations, it wouldn't be a grassland anymore. And so all the species would disappear. And so by any reasonable metric, the coexistence that we see among those grassland species is driven by the perturbation regime. And I don't know of a whole lot of frameworks that currently exist for measuring stability in real world systems that let us take that into account, that let us say basically as the perturbations go up, we end up with a more stable system. And there's a bit of theory about that. So talking about like, what is it? Noisy transitions and stuff like that. And so it's not a new question, but it, I guess, has been the thing that I've been thinking about the most for the last couple of years.
Oh, so
I don't know if that answered your question.
Yeah, no, yeah, I think it does. Yeah, so you're saying like this, that the noise is actually contributing to the stability then?
Right, and that's actually that's what I was trying that I spent much too little time on. But that's sort of shown here in this plot of abundance versus process noise, right? In that for a scaling coefficient of under 2, it means that if you're abundant, you're going to probably not go extinct anytime soon. But if you're rare, you're actually going to go extinct very quickly. And so in this case, in a system that happens to have very low abundance, you'd actually expect longer persistence times for species if you increase the scaling coefficient of the noise function. Effectively, if you make the system more noisy relative to the, if you make the increase in noise steeper relative to the biomass of individual species. And I think that's counterintuitive in comparison to a lot of existing paradigms for analyzing stability in empirical systems.
Okay, so how does that like relate to your CV then? Is it like, does your CV need to increase with abundance, or is it enough that it's constant?
Right. So in this case, it's constant CV would show up as a line here, right? Because that means you have your and I should be a bit careful because I think I was clever enough to plot this in linear space, right? Yeah, this is in linear space. And we're showing standard deviation on the top axis. So any straight line here, a linear line, is going to show a constant CV across this system.
Yeah. Okay.
And so what we sort of know from the Taylor power law is whatever the relationship is between abundance and standard deviation, it's not going to be a straight line in linear space of abundance versus standard deviation. And so in some ways, we sort of know the coefficient of variation is going to have to change. Yeah, so anyway, and so the way that I would think about this is we sort of would have to update our estimate of the coefficient of variation as we move around to different regimes here.
Okay. So like for a population, which one of these two lines is preferable?
Well, that's exactly it. I think it shows that there is no such thing as a perturbation regime that is preferable to or inhibiting of stability. It's the combination of the regime plus the species. And so if I'm a really common species, then this line here with a scaling coefficient under 2 is better for me, because I'm going to be out here where my abundances are going to be, where the perturbations I experience are going to be small relative to my abundance. Whereas if I'm a rare species, I'm actually going to want to be up here. And so even though I would experience massive rates of massive magnitudes of shocks from this function if I were to become abundant, I never do. And so it actually gives me lower intensity perturbation regimes than a system with a steeper scaling coefficient would have. And so it is this interplay between what the stochastic function does and what the species is doing that I think jointly gives you insights into what the stability of the system is likely to be.
Yeah. Okay.
And again, that's not new. I mean, that I think has been one of the main thrusts in Jeff Arnaldi's papers, for example, is to show how you need both the internal dynamics of the species and some information about the perturbation function that's influencing those species.
All right, thanks.
Thank you.
Thanks a lot. Are there any final questions from anybody? Well, it looks like not. Thank you for sticking with us to the end. I guess I will stop recording and say thank you very much, Adam, for a really fantastic talk. It was a really detailed discussion.
Thank you very much again for having me.
No, absolutely.